useful work with like a browser or word processor, everything will just slow to a crawl, as we've discussed. So suppose there were a structure that looked a little something more like this. Enter into the picture something called a linked list, which is pretty much what the name suggests. It is a linked list of what are generally called nodes. What's a node? For now, it's just a chunk of memory. And we can implement these little chunks by way of that C construct known as a struct. So what have we used a struct before thus far? What comes to mind? Sorry? Sudoku. So we had a struct in Sudoku to represent things like the board and the y/x location. We had something for students a couple of weeks ago where we wrapped together a student's name and ID number and house. So anytime you want to kind of clump together some related data fields and call it something new, like a student structure, you can do that. So these squares in just a moment are going to represent what we'll generically call a node. And each of these squares in this picture here stores a number, apparently an int, a 9, a 17, a 22, a 26, and a 34. And this is equivalent for the moment to an array of size 5. So I see 5 numbers, 9, 17, 22, 26, 34. So in effect, I could implement this very easily with week 2 stuff with an array of size 5. But I propose that because I've now drawn the picture in this way using arrows and not by having these numbers back to back to back, as is the case for arrays, it's going to be super easy, conceptually, to insert more numbers into this, to append them to the end, to insert them into the beginning. And there, too, is an advantage. What was really hard in an array? Remember when we had a whole bunch of people up here on the stage when we were doing sorting, and we had to move someone who was over there all the way over here? In the worst case, we had to ask everyone, can you move down? Can you move down? So just to make one swap in the worst case, with an array, we had to do like n-1 steps of work. But suppose the picture were like this, and suppose that in between each number was literally a gap, and there's some concept of an arrow saying the next number's over there, the next number's over there. Well, maybe we could just have squeezed that student and their number into wherever we wanted in this list. So we just need a way of linking nodes together in this way. So odds are these arrows represent what? Yeah, so pointers, right? This is how we've been generically drawing pointers on the blackboard. And so really, underneath the hood, there's some memory addresses and hexadecimal notation and all of that. But conceptually, this is a linked list. It is something like an array, but instead of having contiguous memory, your nodes, your integers, can be stored all over your computer's memory, which is great, because then you don't need to find a huge contiguous block. It can come all fragmented, like from the entirety of your RAM. And it looks like we'll be able to more easily insert numbers into these lists because we can just temporarily move one of those arrows, slot someone else and another number in there, and then fix what the arrows are pointing at. So let's just take a look at what this might look like. I'm going to go ahead and open a file called, let's say, list1.h. And I'll propose this as the container for one of these things called nodes. So we've seen this syntax before, even though we haven't written it ourselves all that much. Typedef does what? If you kind of want to be astute, you can just say, well, it defines a type. Well, what is that? It makes a synonym. One type is a synonym for something else. So let's see what this means here. So we see the keyword struct, and we see the word node. So gedit's being friendly and highlighting all of the C-specific words. So typedef and struct are C keywords. Node is just something I made up. It could be called foo, but by convention, we call these things nodes. And then what composes a node? What is in one of those rectangles? Well, two things. One is an int, and I can arbitrarily call it n, but I could call it anything I want. But then the curious feature is the second thing, the bottom half of this picture here. So for instance, here's n, the number 9. This field here, which I'm apparently going to call next, what is that? Well, if it's an arrow, that suggests pictorially that it's a pointer. How do we write a pointer? Well, with a star somehow. But what is this a pointer to? Well, it's a pointer to the same kind of structure. So we say struct node star, and then we choose an arbitrary word for this arrow. And I'll call it next, just to imply that it's always pointing to the next object. And then down here, I have the word node again, which feels a little redundant. And it is in some sense. So at the end of this statement is the word node. That relates to the typedef. So what this word and this word together mean is henceforth call this whole thing more succinctly node. But remember that C is not so generous. It doesn't look ahead in your code. And so we kind of have a problem, because if I want to create this pointer inside of one of these structures to another such structure, does the word node exist at this point in time? Not really, right? The word node is literally declared here. Well, wait a minute. You also said node here, but this is, again, just because. I need temporarily a name so that I can refer to myself inside of this structure. So long story short, struct node creates this thing. And then the combination of typedef and node here rename it more succinctly from struct node to just node. Why? Why this complexity? Frankly, it's just tedious typing struct node, struct node, struct node all over the place. So now we can just call it node thanks to typedef. But if that's a little unclear syntactically, that's fine for now. Just take for granted that it makes one of these rectangles possible. So how do we now start to manipulate these things? Well, let's rewind just a moment to an example that we already looked at in the past. Recall this thing from a couple of weeks ago. This was a structure that we use to define a student. And there's one syntactic difference. What is fundamentally different about this is there's no word here to the right of struct. Why would I not need to say typedef struct student using the logic from a moment ago? Exactly. And let me tweak the word. I don't mention student inside of the struct, so I don't need a temporary word there. But I could put this here. But again, just as a matter of style, because I'm not using struct student anywhere, I might as well make it more succinct. I do need to say struct, and it's in red because it is an important keyword here. But I don't need to say student up here unless I'm going to refer to a student internally. And this hopefully makes a little bit of intuitive sense, right? If I'm a student object, there should fundamentally, in the real world and in programming, be no notion of next inside of a student object, right? I shouldn't, as a human, have some kind of data remembrance of someone to the left of me. So again, we don't need a pointer there. But we do have two pointers for name and house. So how did we use this? Well, recall students structs1.c, which we looked at briefly a while ago. And this was just a simple example where we created a bunch of structs of type student. We then got the user's ID and the user's name and their house. And then we scrolled down and just yelled out, so-and-so is in Mather, if they were in Mather. So recall this was from a couple weeks ago. And there's only a couple important takeaways for now. For now, recall that this is how we declare an array of students. And for those with prior programming experience, class means like a class of students, not a class of objects. So student class gives me an array called class of student student structures here. So what goes on here, this was the new syntax. If I want to update the ith student's ID number, I use the dot syntax. If I want to update the ith student's name, I use the dot syntax. And if I want to use update the ith student's house, dot syntax. That was new. Then this was kind of old school stuff, strcomp for string comparison. What was I comparing? I was comparing their house against literally the word Mather in double quotes. And then this was important here. I did need to, for good measure, call free on house and name. Why? Because what? Sorry? Because I stored it, but how did I get those strings, name and house? So I used getString. And even though this was kind of some garbage we used to kind of brush under the rug, this was kind of a flaw in our previous programs for several weeks, we revealed a couple weeks ago that getString all this time has, of course, been using malloc. And so now anytime you use malloc, whether directly or indirectly, you must free that memory. Otherwise, Valgrind, this tool I showed a moment ago, that would actually catch. If you ran Valgrind, in fact, on most of your prior programs that used getString from earlier in the semester, almost all of them would be buggy in that they would all have some memory leak. All right, but that's OK. That was deliberate, and those were the so-called training wheels that are now off. So let's just do one modification of this to kind of tie this together also to this week's problem set 5. So this is structs2.c. It's almost identical, but I thought it would be kind of neat to stop writing programs that take in input and then produce output and then lose that output forever. It would kind of be nice if our program, for instance, could store permanently the names and IDs and names of all of the students we type in, right? If we want to approximate the idea of a database, a server that stores information long term, well, it'd be kind of nice if I could use these same ideas now and start saving my work to disk. Just like we take for granted in Microsoft Word or the like, the ability to save, let's do that ourselves. So here is exactly the same code. Give me an array of student structs, populate them using getInt and getString and getString. But down here, Go ahead and say whoever's in Mather just to be cute. But now, let's save these students to disk, which just means save a file. So how might we do this? So we could do this in any number of ways. Microsoft back in the day decided that a doc format, DOC, is going to store your essay and your boldfacing and your table of contents in a certain way. Similarly, we as programmers here have to decide how are we going to store something like a student ID and name and house, perhaps for multiple people in a file. So you could actually do this in a bunch of ways, but we decided totally arbitrarily that we're just going to store these IDs, names, and house one per line in a text file, just so we can see it. But this is, of course, a very unsophisticated approach, but it will allow us to write files to disk. So let's see this. The very first line of interest is this thing here. So fopen, you might guess, is file open. And we've not had to use this ourselves unless you already dove into problem set 5. But as the name suggests, it opens a file. What's the name of that file going to be? Arbitrarily, I called it database. It could be called foo, but again, I chose database. And then just take a guess. What does quote unquote W mean? So it means write. So it means write this file as opposed to reading it. So you can actually use the same fopen function to read files in, but for today we'll just do it with W. As an aside, you might see in various books or tutorials people saying WB for write binary or write ASCII. Realize that on the appliance and on most modern systems, it suffices just to say R or W. You don't need to worry about the B, just FYI. So why do I check for this? If FP, which is just generic notation for file pointer, if it equals null, when might something go wrong related to writing a file to disk? Why might fopen, just conjecture, return null? Sorry? So database is missing. Maybe that file doesn't exist. In this case, that's going to be OK, because what's nice about fopen is if you're writing a file and it doesn't exist, it will create it for you. But a good thought. That would be the answer if we were trying to read it back in, certainly. Yeah. Yeah, so if your disk is full, right? If your hard drive is just overflowing with other files and you just don't have enough space for any new file, fopen could return null. Other, maybe more technical problem? If you've done something stupid or accidentally, like change the permissions on some folder, or you're in some folder on the system that doesn't belong to you, it's someone else's My Documents folder, for instance, well, fopen might return null in that case too. So in short, if you lack the ability to write a file, you're just going to get back null. But what is it you're going to get back? Well, FP is of type file, and it is in all caps just because someone decided to make it that way. And it turns out a file structure, F-I-L-E in all caps, is some kind of structure, not unlike conceptually a student structure, inside of which is a bunch of stuff. And that stuff is generally hidden from us. But you can think of a file kind of like a cassette tape, if you even remember these things. A cassette tape, of course, has a whole bunch of tape inside. And when you play a song on a cassette tape, these two things turn and the tape physically moves. A file on a computer system obviously has no tape, but conceptually you read and write it in the same way. When you open a file with fopen, it's like taking out a cassette tape and starting at the beginning of that tape. And as you start to read from the cassette tape or read from the file, it's like advancing the reading head, the cursor, so to speak, or the file position indicator, so to speak, on that file. And if you write to a file, similarly that happens. Now this is relevant because in problem set 5, one of the challenges is to enlarge a bitmap file. So you have to take a pixel and double it or triple it and so forth. So realize that one of the challenges that arises in problem set 5 is, well, if a file is being read from start to end, just like a cassette tape, well, what if you need to kind of rewind the tape and go back and reprint those same pixels, re-output those same pixels? Well, there's functions like fseek, file seek, which can help you do this. There's frewind, although that's typically overkill. But there's other ways altogether, as Tommy discussed in the walkthrough involving arrays and just remembering some of those bits. But in short, for now, this is a pointer to a file structure, and it's not clear to us just yet what's actually in that file. I accidentally quit there, so let me go back to structs2.c, and we'll finish this story. So how do you write to this file? Well, if I get